All right, for this last one, we are given a velocity versus time graph, and we have to change the velocity versus time graph into the position versus time graph and into the acceleration versus time graph. I'm going to start with the acceleration versus time graph because all of these lines are straight here, which means it's going to be a lot simpler of a process. So let's get to it. For the first segment of the velocity, it looks like our velocity is steadily increasing for the first 5, 6, 7, 8 seconds. So that means for the first 8 seconds down here to 8 seconds, our acceleration is, well, it depends on whatever our slope is, because the slope of a velocity versus time graph will be the acceleration. We're going up 8 and going over 8. So we have a slope of 1 for the first 8 seconds. For the next 8 seconds, we have a slope of, it looks like we're going down 16 and we're going to the right 8. So that means we have a slope of -2 for the next 8 seconds. There you go. And then for this last part from 16 to 20, it looks like, what's our slope here? Well, we're not going up, so we're not rising, so we have a 0 acceleration. And that's all you have to do. Remember, you have the option to put in these vertical lines, but you do not have to. I kind of like them because it just makes the graph feel more complete, but really it's not necessary. All right. Nice and easy. Time to translate from velocity versus time into position versus time. So how do we get position versus time from a velocity versus time? That's right. We remember that the area under the curve for a velocity versus time graph will give us our change in displacement. So I kind of spoiled the surprise there by coloring it in. Bad, Mr. Scapetus. There we go. I'm cutting this into pieces that I know the areas for. I don't know a lot of area formulas, so I like to keep it to triangles and rectangles. So here we know that our area formula for a triangle, area for anything, I guess, is length times width, but for a triangle specifically, we're going to cut that in half because of this. What is a rectangle but 2 triangles? So to get this, our length is 8, our height is 8. 8 times 8 is 64, divided by 2 is 32. So for the first 8 seconds, still the same time, we're going to get up to 32. But wait, that's not right. 34. Why are we going up to 34? Because we're not starting from 0. In the problem, take a look, x naught is 2 meters, so we're pushing everything up 2 meters. Okay, so it goes from here to here. Is this going to be a straight line? Well, remember, all the shortcuts that we talked about remembering before. When is it curved? When is it not curved? All of those things. In this case, our displacement is growing, right? So there is a curve there to it. So it's going to be this shape. For the next segment, we're going to find the area of this triangle again. The rise or the height is 8, and this is 4. That's right. 8 times 4 is 32. 32 divided by 2. 16. So we're increasing by 16 for this time frame. And it looks like the time ends at 12 seconds. So at 12 seconds, 12 seconds, we're going to increase all the way on up to here. Now, because we crossed through the 0 velocity and we continue on, that means our direction is changing. So now we're going down into negative world down here. So that means if our direction is changing, it's going to do something along those lines, come back down. Luckily for us, our graph only goes up to what we need. What luck! So we're going to go from here, 12 to 16, which is 4, and then our height is 8. 8 times 4, 32, again divided by 32, so that's going to bring us back down to 34 at 16 seconds. And I'm trying to make sure it's in here properly, but this is a nice curve. Please don't ever retrace over your graph like I'm doing. That's bad, Mr. Scapetis. By doing that, you're not showing where your graph really should be. There we go. Now I fixed it. So that's what it's looking like. And then for this last one, it's length times width, which again is 4 times 8. So it is 32. So we are going to come back down to 2 and finish off this graph to have it look like that. All right. That's it. Oh, wait. No, it's not, Mr. Scapetis. We got to do this motion diagram. So our motion diagram, you're going to just take these points of displacement at each time interval. So every 1 second. So we're starting off at 2 meters right here. And then for the next second, where are we? You would look at your graph and you would say we're here. For the next second, where are we? We're here. We do have an acceleration, so you're going to notice spacing out of these dots. I'm not going to go through and put in 20 dots, but you should know how to do that. So again, I'll do one more. 1, 2, 3. You're at 8 dot. 8 there. And then 4, you're at 11. And then as you keep going, you're going to notice them start to space out. I think because you've got positive acceleration here, you start with the dots close together, and then they're going to grow, and then we have a negative acceleration, so they're going to slow down, bunch up again, and then they should grow back again. That's it. See you next time.